and I won a Nobel Prize.
How much of that was your life?
The honest answer is that work was done in a few weeks. It's maybe less than 1% of my life. We have to expand our vision of what reality is. In consciousness, we can travel in time, construct alternate futures, whereas in physical reality, we're kind of stuck.
Do you think it's likely for you to win another Nobel Prize before you die? First question, who are you?
I'm Frank Wilczek. I'm a theoretical physicist and author and intellectual explorer. And I have various credentials. I'm a professor at MIT, also have positions at Arizona State and Stockholm University. And I also have connections in China, where I'm chief scientist at the T.D. Lee Institute and also at something called the Wilczek Quantum Institute, which I'm very proud of. And I've won a Nobel Prize, and I'm still going strong, I think. I'd like to think, right?
Do you think it's likely for you to win another Nobel Prize before you die?
It's not out of the question. And, some of the things I've worked on have really borne fruit, and others and have not been recognized yet. And others depend on nature. We have, I think, a very exciting prediction for what the dark matter is that solves important problems, also not only in cosmology, but also in fundamental physics. And I've been working on this called axions more or less on and off for 40 years and contributed to various all aspects of it, both the original concept, the application to cosmology, and now the design of experiments. So that would be another one. I would like to think that would be for sure if it's actually discovered. Big if.
First of all, we need to address, because some people will be a bit worried that why I do have a headset on. I'm trying for 30 days to break the world record of the longest human that put a VR headset on. And I wanted to tell you as well that this is the first mixed reality headset. So now I can control stuff with my fingers. I have like different tabs open, and I can navigate the real world as much the online world with this VR headset, which is a good experiment. It's been 20 days that I wear it, and it's been a bit tiring and challenging. But yeah, I just wanted to make sure that people understand why I'm not like a crazy person. I'm a crazy person partially. So let's continue with our conversation, and maybe we can mix this together. So do you think the real world that we see is the actual real world that is the truth, what we see with our eyes?
Well, I think our senses are limited in well-known ways. There are possibilities for illusions. There are possibilities for hallucinations. But I think the broad intent of your question is empirical reality as revealed mostly by our senses, but also by instruments that we devise that can tell us more about what's going on in different things that our natural senses don't take account of. I think that's all there is. And if so, people, scientists, physicists in particular, have worked very hard to construct a coherent picture of the world, and been very aggressive about applying that picture in different circumstances And if there's something we encounter that we don't know, we haven't been included, we include it. So dark matter now is a good example. The cosmologists have found something that we don't know what it is, and we don't know really how to see it, except indirectly through its gravity. So that's a nut, but it's an element of reality because it exerts physical effects, and we're on the trail of more physical effects to get a complete picture of what it is, so we can bring it into the overall picture of the world we have. So that's a long now. So physical reality, I believe, is accurately conveyed by the laws of physics, and but there are other realities, if you like, sort of emergent realities, the world of ideas and mind and philosophy, if you like, of abstractions, where the notion of whether the concepts that arise there exist or not is a question that's been debated for millennia. And does the number two exist? I think it depends very much on...
What do you mean by that? Does the number two exist?
Well, we know many examples of two things. You can have two of this, two of that. But there's also a concept, two, that appears in mathematics. Does that exist? Is there just an abstract Platonic two that is independent of any particular realization of it? And clearly there is. We can use the word sensibly and do useful things with it, with that abstraction. Whether it exists or not, I think depends on what you mean by exist. So this is one of many cases in which language can be very confusing, because the words we use are ambiguous. And although when you ask whether something exists, that may seem like a straightforward question, it's really not, because the word exist is used in different ways. And
so do you think the number two the concept exists or not?
Well, the concept certainly exists. We use it every day. Whether it exists in the same way as a lump of coal exists, clearly it doesn't. It doesn't participate in the laws of nature in the same way. It doesn't feel forces or move around. So we just have to expand our vision of what reality is beyond physical reality to take into account concept realities. I think that's true.
Interesting. So since we are in this topic, I wanted to take your take as well on what Donald Hoffman. Do you know him?
No, I'm not sure I do, but maybe if you told me something about him, it might jog my memory.
I read his book, and I think he has a reference about your work inside. So he talks that he's in a way idealist. He believes that this world is like basically consciousness and not the physical world that we see. And I'm curious to hear your thoughts on that, since we are in this topic, that what exists anyways.
Well, we can make a very coherent picture of the world based on the idea that there are entities out there that behave in predictable ways according to the laws of physics, which are ultimately simple, although in their application sometimes complicated. And that the laws that they follow are kind of abstract mathematical laws, whereas the laws of mind and consciousness, on the face of it, seem very different. I mean, in consciousness, we can travel in time. We can go back into the past and relive experiences. We can construct alternate futures and imagine them. Whereas in physical reality, we're kind of stuck with just, well, physical reality. It doesn't have that property. Doesn't have those properties. It's very, very limited in ways that consciousness isn't. So I think it is useful to make a sharp distinction between consciousness and physical reality, just because they behave in very different ways. Now, so that's the first order. That's the rough picture. The more detail, a richer picture that's important to add is that I believe that consciousness is a property, can be or is actually a property of matter. So it too can be subsumed into the idea of physical reality. So I'm much more sympathetic to kind of the opposite idea that consciousness emerges from matter rather than matter emerging from consciousness.
Which one you support more? Matter emerges from consciousness, or consciousness
emerges from matter? Consciousness emerges from matter. Mind emerges from matter. Yes, I think so.
And why you choose this more likely scenario?
Well, I think, well, first of all, there's just the empirical experience of science being able to understand more and more of things that were once thought to be outside the realm of science. I mean, there was or to require additional principles, rather, in addition to the law of physics. At one time, people thought that biological materials were made of different kinds of things than ordinary materials. Now we know that that's not true. At one time, people thought that there were vegetative souls, that's Aristotle's term, for things that governed processes like digestion and metabolism. Now we understand the molecular basis of that. We understand the molecular basis of heredity. We understand a lot, although not everything, about the molecular basis of human minds. We certainly understand a lot about perception, especially visual perception. And so far, in literally thousands, tens of thousands of different delicate experiments on neurons, on brains, on thought processes, it's been adequate to, there's been no evidence against the idea that there's ultimately a molecular basis of all that. And as time goes on, we've understood more and more at a molecular level. Now, so that's sort of a general picture. A more particular picture, a more particular point is that when we do experiments in science, in particular in modern physics, we can look for very, very delicate effects that we have to make sure the conditions are just right. You have to shield from electromagnetic radiation and shield from shaking of the earth, and maybe put things in a vacuum and make them at low temperature, take all kinds of precautions in order to isolate the delicate behavior that's predicted theoretically. But one thing that people have never had to do is make corrections for what people were thinking. So there's absolutely no evidence that you need to worry about non-physical effects like thought waves or telekinesis or things like that. That would be a great discovery if it were to be discovered, but it hasn't been discovered. And then finally, I would mention that we're constructing minds. Computers have become more and more capable and are doing things that once were thought to be properties that only conscious minds could do, like this, or very great intelligences. So it was once thought, for instance, that playing chess well would require great wisdom and powerful minds, but now computers do it better than humans. And there's no secret about how it's done at a molecular level. Those kinds of minds we definitely do understand at a molecular level. In fact, we built them according to the laws of physics. And similarly, our great sensors that can reproduce sensations of the world better than human senses. Similarly, now with ChatGPT and things like that, more and more things that were once associated with minds and souls are being reproduced in material systems that we understand thoroughly at a molecular level, and in fact design. So all of those things, I think, argue those. I think the three basic powerful arguments: the argument that we're making progress and so far no new effects, that we've never had to correct for mind waves, and that we have examples of emergent minds that are very impressive. All of those make me feel pretty confident that human consciousness, also human minds, are emergent properties of matter. That doesn't mean that they're not great. I mean, they are great, but matter is great. That's one thing we've learned, is that matter can do all kinds of weird and wonderful things, and mind is one of them.
Yes. But consciousness is great as well, because imagine if we didn't have consciousness to enjoy all this stuff and feel the redness of the red. So both are great.
Yeah. Oh, there's nothing. Yeah, no. To make a full account of the world without using the concept of consciousness would be very difficult. So, even I've said that I believe that ultimately everything is grounded in the laws of physics. I'm open to counterexamples, but I don't know of any. And but on the other hand, that's not necessarily a useful way of thinking about complex objects or emergent properties. So when we relate to other people, it's not useful to them to think of them as collections of quarks and gluons and photons and electrons, even though probably ultimately they are. That's the deepest way to understand them, but it's not practical. And we use concepts like personality, drive, will, and consciousness to describe how such things behave, including ourselves, including our own experience. So and it would be silly not to use those concepts.
So I want, first of all, to tell you a bit about me. So I just finished high school, so I'm very stupid. And you are probably the cleverest, one of the cleverest people. I am having a conversation. So I want everyone to understand that. And I apologize in advance for some stupid questions that I will ask.
They're naive questions, not stupid questions. So it's great. You'll learn.
So first of all, I want you to explain me. So what is your contribution to the science as we know it, and you receive Nobel? What is the thing that?
Okay, so the work that got the Nobel Prize was figuring out what the basic theory
And also,
what
before you start explaining that, I think it's important to mention how much of that was your whole life. It was like 10% of your work. It was 1% of your work. The Nobel Prize, the work that you received.
Well, that's a little bit complicated, but I think it's the honest answer is that work was done in an intense period of a few weeks. So it's maybe less than 1% of my life, significantly less than 1%.
Okay.
So what we did was figure out the equations, the basic theory of what's called the strong interaction. Physics now thinks there are four basic forces of nature, and they are electricity and electromagnetism is one, gravity is another. Those are fairly familiar forces. But at the beginning of the 20th century, when physicists began to study the interiors of atoms, they discovered that those laws were inadequate, needed additional laws. And in fact, we needed two additional interactions. This is summarizing a lot of experiment and phenomena. But two interactions were necessary in order to deal with all the phenomena of nuclear and subnuclear physics. One is called the weak interaction, and that I didn't have much to do with, but the other is called the strong interaction. The strong interaction is the basic theory of what holds atomic nuclei together. And the way, as it developed, we learned that the deep structure is that the protons and neutrons that in elementary treatments are said to be the building blocks of atomic nuclei are really made out of smaller, more basic things called quarks and gluons. And it's the quarks and gluons that obey relatively simple equations. And those are the equations I discovered. And so then you have the job of building back up from quarks and gluons to atomic nuclei and matter as we know it. But knowing the basic theory has led to tremendous applications in understanding what happens at accelerators and understanding cosmology and in attempts to understand neutron stars and attempts to unify the different forces of nature. So it was a very fruitful thing to figure out what the basic equations are. So that was actually the first serious piece of work I did in physics, and I was 21 years old at the time, working with David
How
Gross.
old? 21. 21.
Yeah, I was 21 at the time, right. I was working with David Gross, who was a more experienced physicist. He was 31, but yes, we were young in those days. And so that was my first piece of work. And so discovering the theory and then working out, especially the applications to cosmology and to unification of the different forces of nature. I've done a lot of things. My publication list has, I think, close to 600 entries now, so I won't describe it all. But let me just describe a couple of highlights. One big highlight is the discovery that there are new forms of what's called quantum statistics. Now, this unfortunately requires quite a bit of explanation, although it's very basic in physics, to sort of put it in context. One says, and I did say earlier, that there are four forces of nature, four basic forces. I'll remind you, was gravity, electromagnetism, and the strong and weak forces. But actually, in order to account for how the world works, there's another aspect of the laws of physics in quantum mechanics that I think in many ways just deserves to be called a fifth force. And this is something called quantum statistics. The name is kind of bizarre, but that's the name. What it means is that what people thought it meant for a very long time is that there are two different kinds of particles. One kind called fermions, and that includes electrons, neutrons, and protons that repel each other. They have an additional kind of force that when you have identical particles like two protons or two neutrons or two electrons, they feel a repulsive force. They don't like to be put in the same quantum mechanical state, technically. So that's like an additional force. That's not an emergent feature of quantum theory. So it comes for free in quantum theory. It doesn't have to be added into the structure of the interactions, but it's very profound. It's what's responsible for the periodic table, for the existence of white dwarfs and neutron stars, and many other things. So that's one class. The other class is bosons, and photons are the outstanding example of bosons, and they feel an attractive force instead of a repulsive force. And so that means that's responsible for lasers, where photons stick together and all move in the same direction with the same color and so forth. It's also responsible for superfluidity, superconductivity. So it also features very importantly in nature. So quantum statistics is an additional force, and for a long time people thought there were just two kinds. But what I and others realized in the early 1980s is that if you look not at particles in free space, but at particles inside matter, so by particles I just mean concentrations of energy that are stable, that have an identity, that move around as a unit inside matter. So sometimes they're called quasi-particles, but they're the same thing as particles. If you lived inside the matter, that's what you would just call the particles. That there are other possibilities, and I called these anyons because there are many more possibilities than just two, bosons and fermions. And anyons are very interesting because they have a kind of memory, and that now, and it's only in recent years that people have gotten experimental evidence for the existence of these things. So that was very pleasing and dramatic just a couple of years ago. But also it's turning out that they might be useful for quantum computing. The fact that you have these particles with memory gives new possibilities for constructing, for new possibilities for computation that people are exploring very actively now. So that's the short story of anyons. And then I'll just add one more. That's axions. Axions are so far a hypothetical particle, but becoming very popular as a hypothesis for a new kind of particle that should exist. And because axions arise in understanding the fundamental laws of physics more profoundly. There are aspects of the so-called standard model that, although the standard model is very successful empirically, there are aspects of it that are kind of lopsided and ugly, but they can be made beautiful if you add the axion. And then we discovered that axions have very unusual properties for particles. They're not very much like any other particle. I guess they're most like photons, but they interact much more weakly than photons, and they have a small but non-zero mass, unlike photons, which have mass 0. But then when you work through the cosmology, of the Big Bang, you find if the axions exist, they would be produced and hang around. And in fact, they would have all the properties that astronomers need to provide the dark matter that they need. So, so now it's a important idea that the dark matter that astronomers have found, don't know what it is, but there's a lot of it, 6 times as much as ordinary matter, that it's made out of axions. And because we can say a lot about the properties of axions, if they exist, we can design experiments to look for them, and it's very difficult because the axions are predicted to interact very, very feebly with ordinary matter. But in recent years, as technology has improved and our understanding has improved, it's becoming feasible. So that's very exciting, and I've been very actively involved in all aspects of the axion story. Yeah. So those are 3 highlights of my career.
So very interesting. So as time goes, because you started very early in these things, you become more excited, less excited, more. Did it happen to you that you lost the interest at some point, and then you started going too much partying?
To be honest, I've had ups and downs. There are times when I'm more excited and times when I'm less excited. I think right now I'm definitely at a high point in my career because anyons were just discovered experimentally. QCD, this theory of the strong interaction, has flourished, and there are very interesting new developments. It's in trying to understand neutron stars and atomic nuclei, and it's remained very, very interesting and important. And axions, it's at an extraordinarily exciting state because the experiments are just becoming feasible to see whether the basic idea actually applies to the world. So all those are exciting, but maybe the most exciting thing is that I'm having fun. Over the years, I've worked on many other things besides those, and right now, I'm working on ideas about superconductivity, ideas about biology, actually, and aspects of symmetry in biology, and a classic problem of understanding what's called tunneling in space and time that I think I'm making a lot of progress on. So all those things, plus the fact that I am enjoying working with collaborators all over the world, including some young people who really, are enthusiastic and bring joy and youth into the picture. I don't think I haven't. Yeah, it's a great time for me in my career. Yeah.
Can you describe me on those low moments that you described? What was happening? It was not as many discoveries, or it was some personal thing. What was?
Well, I'm not going to enter into the personal things, but that's not. But personal things. Like many people, I've had ups and downs. Although I've been blessed. I mean, I just celebrated my 50th wedding anniversary, and I have many friends around the world, and so that's okay. Although to get there were ups, there were struggles, and for a long time I didn't have much money, and but it's fine now. It's fine. Well, there are many practical worries and raising children, all these things. But the real, for me, the real down periods are when I have some idea that I'm very fond of turns out to have problems, which is not rare. Most ideas in research at the frontiers of knowledge don't work. And usually you can find out pretty quickly if something is not going to work. But sometimes if it almost works or somehow is very interesting and the flaws are subtle, you might have to invest a lot of time and effort and hope in something that ultimately is disappointing. So that can be hard. And also frustration. I mean, the Axion story has been going on for 40 years, and we still don't know the resolution. But for many years, nobody was very much interested because it appeared to be the experiments appeared to be too difficult to see whether it existed or not. Some easy experiments were done, but they didn't find it. But then the more challenging experiments, it's taken 40 years for them to become feasible. Anyons also, similarly, for a long time, nobody much was interested. There was an initial flurry of interest when the concepts were first introduced. But then again, the experiments kind of stalled, and the impetus from the possibilities of computing wasn't really taken seriously. But now those things are really flourishing. So it's much more fun when a lot of people are excited about it, and money is flowing in, and experiments are getting done. So, but that wasn't the case for a long time. So there have been dry periods when the good ideas seem to be finished, and the new ideas were no good. so that happens. Yeah.
I'm curious to hear your thoughts, because you've been around the block for a long time, on the evolution of science through the years. Do you think now, with all the tools, the internet, how do you observe the evolution?
Well, there are many things that have changed for the better. The possibilities of international collaboration are much simpler now. You can communicate with people around the world, and I do. I have friends around the world, and collaborations ongoing with distant people, and that's really nice. It's an expanded universe in a real sense. The tools that I use of calculation on computers. Most of what I do is still analytical, but some of it does involve a numerical component, and I really enjoy doing that when I do it, and it's very powerful. In the early days, when we wanted to use a computer, we had punch cards, and it was very slow and painful. Now it's a very different kind of experience. And then, of course, the experimenters gotten much more versatile in techniques. Cosmology, when I was a graduate student, cosmology was still a very, very data poor subject, and that's flourished. On the downside, I would say particle physics. We're kind of the victims of our own success. We had so much progress, such dramatic progress, and reached such a perfect theory in the 70s and early 80s that it's been very, very difficult to improve on it. So the pace of discovery has really, really slowed down in some branches of physics, but other new ones have cropped up and flourished. And I think if you take it as a whole, it's more exciting than ever. Yeah.
So it's more exciting than ever. Do you think also there is a lot more people, young scientists in comparison, population-wise, being interested in this topic?
I think so. I think in absolute terms, they're almost certainly, but relative to other branches of science, probably not. other branches of science have grown perhaps more rapidly than physics. Even within physics, cosmology has grown more rapidly, I would say, than fundamental physics. And now quantum technology is growing more rapidly. But also, if you take physics as a whole, compared to biology, compared to computer science, it probably is not as dominant. It's not dominant in the way it once was. Many of the brightest people go into other things. When I was a graduate student, it was like a point of pride that if you were a smart guy or gal, you did fundamental physics. That was the most challenging thing. That we still had the glamour of Einstein and quantum mechanics, and so and new things were being discovered, and it was really fantastic. But that's slowed down, and there's more competition from other fields. So as a proportion, I think fewer people are in it now.
Interesting. Let's go for a bit of a fun question that my viewers want to know. So they are asking if when you got the Nobel Prize, life got easier. Like, for example, a lot more people wanted to collaborate with you, or a lot more people, or you had a lot more girls. I don't know. Like,
now, as I said, I've been married now for 50 years to the same woman. So the girls' part, even if there were, I wouldn't talk about it. But but the spirit of it is, let me give a nuanced answer. So within physics, by the time I got the Nobel Prize in 2004, I was already a very established researcher, and, in all modesty, was famous worldwide, and people were eager to collaborate. That got accentuated with the Nobel Prize, and especially sort of beginning students are very impressed with the Nobel Prize. So they pick up, it's kind of it's like a certificate of approval a credential. It's a credential. So that's immediately recognized and people respect it. But so, within the research community, it didn't make all that much of a difference, I would say. But at the edges of the research community, that is sort of other fields of science or young students, it's a credential that people recognize, and they take you seriously and want to talk to you. And so, to an extent that wouldn't be true without the Nobel Prize. And to the outside world, the world outside of science, or even outside of physics, it's a much bigger difference, because again, because it's a credential that not many people have, and it's enormous prestige. So, publishers, podcasters, people want to talk and hear something that's authoritative, and so those kind of opportunities open up to a much greater extent once you have a Nobel Prize. That's it.
So what it did to your ego? Did you thought that you are the cleverest man in the world, and it affected like your way to do science? Or
no. Well, I've been very fortunate in that I had early success. When I was in school, I won prizes for academic success. I skipped many grades, so so I had considerable confidence. But I did hit a rough patch after I graduated from college at the University of Chicago and went to Princeton as a graduate student. The transition from being a student to being a researcher was very challenging for me because I really didn't. I sort of changed fields, although that's not the right way to describe it. I went there as a graduate student in mathematics, but I didn't want to do mathematics. I wanted to apply mathematics, so I had to figure out what I was going to do, and so my self-confidence kind of evaporated at that point because I was lost. I didn't know what I wanted to do, and I think I was, from the outside, it looked like I was kind of floundering, but fortunately, I found a thesis advisor, David Gross, that was really good, and problems to work on that were really good, and that's what became the Nobel Prize work. Well before the Nobel Prize, the work was widely appreciated in the research community. People didn't necessarily accept that it was correct, but they did accept that it was very clever, and it made my reputation, and I gave talks around the world, and so I had a lot of early success, and that's very important. I think I said confidence is a very important asset for a researcher, because as I mentioned, most things don't work. and even things that work, often they seem not to work for a long time. You have to stick with it and have the confidence to keep going with something that's and also without confidence you don't take on essentially new problems that are the most important ones, the most challenging ones, where you don't know what the outcome is going to be, and so I got confidence. I guess, first, I have confidence from all the way back because my mother loved me, and I got a lot of support from my family, and then from teachers, and then from early success. All those things gave me a lot of confidence, and so the Nobel Prize was a boost, but it was not really the crucial boost, and. So maybe I'll just leave it at that. So I already was very confident, and the Nobel Prize helped a little bit.
Because of a mistake that I did with my Wi-Fi, we stopped recording the rest of the conversation, and I apologize to you guys and to Frank of my mistake. I will try to improve in the future and not make these mistakes again. And I just want to say a big thank you to you guys that you watched this podcast so far, and to Frank for being generous with his time and teaching all of us. I love you all. Until next time, bye-bye.